modeling conductors and insulators. Most people have an idea of what is the difference between a conductor and an insulator. A conductor allows current to flow easily, while insulators, which are technically called dielectrics, don't. Electric charges are absent in insulators, while conductors are used to make electrical equipment. Good conductors are like silver, gold, and copper, while good insulators are glass, rubber, and wood. So we need to be more detailed. So in my attempt to provide more information about their differences, I will use a toy model that hits the three important features of the quantum mechanical model. And I'll talk about these in a moment here, but it comes down to the available electrons, the binding energies, and something called the band gap. So let's look at a picture of this. So here is my toy box model. So when I think about a box model, what you want to imagine here is that we have a box with an opening at the top. So I imagine that I have a box that's going to look something like this, and then I have the opening here. So this is the box that I'm going to try to look at that. And one of the things that you're seeing here is that here's the opening, but this is the lip of the box opening. So what I'm going to place in this box is that the box will contain a number of BBs. In other words, small ball bearings. that will experience a shaking force. In other words, once I put the BBs into the box, then with my hand, I'm going to start shaking the box. So this model is going to attempt to explain the behavior of the electrons. So here's what we see here. So the first thing that we should look at is that we need to talk about the number of BBs. And what this does here is this is the number of available weakly bound electrons. Two. So then we need to look at the distance to the opening. So the distance to the opening, what this is going to represent is this is going to represent the binding energy caused by the nucleus. And then the third thing here is that we have to look at the size of the opening. And what this represents is that this will represent the band gap is how electrons are transferred between atoms. So in this toy model, properties of conductors and insulators are as follows. So I need to list the number of available electrons. We need to talk about the binding energy. And we need to talk about the band gap. So then I'm going to have my conductor here, or conductors, and then I'm going to have my insulators. So let me set up this table. So here we go. So now let's start thinking about this. Picture-wise, I imagine that I'm going to try to model conductors here. And I'm going to model insulators over here. So when I start to look at the boxes, I imagine that I'm going to have a box that's going to look something like this. So if I look at my box, I'm going to do this. And so I'm just going to copy this exact same box over here. And then you could see that I have that. So now what do I see here? What I see is the following thing. When I look at the conductors, they have numerous electrons. So when I'm thinking about this, I imagine that I have a lot of electrons here. So let's say that this level right here. So in here, I imagine that I have a lot of electrons. And in fact, there's a name for these. This is called the sea of electrons. And so I have a lot of these electrons. So they're numerous electrons. On the other hand, when I look at insulators, they have very few. So I could imagine that if I'm looking at the number of available electrons, there's not that many. So now I need to create the binding energy and the band gap. So if I look at this, here's what I find. The binding energy is the energy to the opening of the lip here. So if you look at this guy right here, this represents the binding energy. So if I was to draw a well for this, this is how the electrons get trapped. And you can see here that this guy represents a relatively shallow well. Now, if I do the same thing over here, what I'm going to find is that this guy has a small opening at the top. So when I look at this guy, here we see that there's a large distance, which tells me I have a large binding energy to get those electrons out. So now if I look at my well here, my well then goes all the way down to here. And you could see that it's going to take a lot of work to actually remove one of these electrons here. So in this case, you can see that this has a low binding energy because the well is shallow. This has a high binding energy because it's a very deep well. So now the last thing that we got to talk about here is the size of this opening. And this is called the band gap. And you can compare the two band gaps, and you could see that there's a big difference between the two. In other words, the band gap on conductors, this is very large, and here, this is really small. So what does this all mean? So if I start, by the way, I should come clean here. The band gap is just the opposite in the quantum mechanical model. This is why I call this a toy model. The band gap is actually small for conductors, and in insulators, the band gap is large. But this is a toy model, and it's a box model, and it's not the full quantum mechanical model, of course. So what happens now? So to remove the BBs, remember, these are the available electrons from the box. One must apply a shaking force. And what we mean by that, there has to be some electrical interaction. So in other words, I'm going to now provide a shaking force. And as I provide a shaking force, what actually happens? Well, if it's easy to remove, for conductors, it's easy to remove BBs from the box. That tells us that this box is a conducting box. In other words, it's easy to transfer. However, if it's hard to remove BBs from the box, then this box here is an insulating box. So then if we start to transfer this, if I have some electrical interaction, and it's easy to remove the electrons, and these are going to be the electrons in atoms, then I know it's a conductor. If it's hard to remove the electrons from the atoms, then I know it's got to be insulating. So we've already modeled this, but we want to modify how we look at potential wells. So picture-wise, how does one visualize insulators and conductors? In atoms, we typically use potential wells. So the quantum mechanical model deals with potential wells. We've already said this in the previous chapter, but let's re-say it again here. So in atoms, the positive nuclei creates a potential well to bind electrons, where the depth is the binding energy. Let's define the 0 point. And the 0 point is what we call the ground. So when I look at the ground, I'm going to say that I can have a little tiny well that then traps my electron. And this whole area in blue, we will never find an electron here. So this region right here, this is our forbidden region. So this tells me that we have a very small binding energy. On the other hand, well, let's continue with this. So this tells me that I have a shallow potential well, which then tells me that I have a lower binding energy, which then tells me it's easier to remove. Now I can do the exact same thing, but now I'm going to have a deeper well. And let's say it goes this deep. Again, this is our forbidden region. Here's our trapped electron. And what we're seeing here is that this guy has a deeper well, so it has a higher binding energy. So this is a deep well, and as a consequence, it has a higher binding energy. Therefore, it's harder to remove. So now we could start talking the difference between insulators and conductors. So now let's look at insulators. So the way we represent insulators here is that we say here that so we use deep potential wells that separate electrons into individual wells. This makes it harder to remove. And what do we mean by remove? They have higher binding energies and share. What do we mean by share? They have a smaller band gap they share electrons since insulators have the following properties. They have lower number of available electrons. They have higher binding energies, and they have a smaller band gap. So picture-wise, I imagine that we have something like this. So I imagine that we have deep wells. And you could imagine that there's numerous of these. And so again, these are the forbidden regions. You will never find electrons in these regions. So then I come in with my electron and I go, yep, there they are at the bottom. It's not easy to share these electrons because they're all individually separated out. That's what I mean by an insulator. Now the conductor is going to require more work. So let's look at that. Okay. We model conductors with a single shallow potential well. With numerous available electrons. Due to their large band gap. So we want to do this in steps because it can get tricky. Okay, so let's do this. So the first thing that we want to do is that let's talk about step one. We want to talk about the copper atom structure. So we've already talked about the copper atom. So remember, I'm going to draw this in the Bohr model just as a visualization tool. So here's what I imagine. We have 4 energy levels, and they don't look like this at all. And what we're seeing is that we have our nuclei right here, and it has 29 positive protons. So this is show 1, 2, 3, 4. We know that there's 1, 8, 18, and then we have 1 electron in that thing here. So when I'm looking at these, we have a number of inner electrons in these guys right here. So now let's go to our potential well. So now I'm going to go to the potential well model. And when I look at the potential well model, it looks like this here. So I'm going to model a box, but it's not really a box. So I imagine that I have something like this here. So my box, how am I going to draw this? Let's say I'm going to draw it something like here. Now, so I imagine that I have the lip. Here, I gotta think a little bit deeper on this. So I'm going to look at this guy right here. And I'm going to say that this here is the skin of the metal. Okay, so right here, I'm going to say that this piece right here, this is the skin of the metal, or the conductor, I should have said. And so what you're seeing here is that if I was to draw this a little bit better, oh, I shouldn't have called it the skin. I should have said that this was the surface. But the surface has some thickness. And so when I'm looking at this, I'm going to imagine that I have this piece right here, and this represents the inner electrons. So I imagine that I have a series of electrons here. Now, it doesn't look like this, but I'm just trying to model it a little bit nicer so you could possibly visualize this. So in here, you're seeing that, you know what, I'm going to move this over because I'm going to run out of space. You're seeing here that these are the inner electrons that are not available. The only electrons that are available are the weakly bound electrons. So then I'm going to come in here and I'm going to shade this right here. And this here is the region that we're talking about. And these are the available weak electrons. And so it's right in here. And so I imagine that I have my electron right here. And maybe I'll try to draw that a little bit darker so that it stands out. And what you're seeing here is that this here represents the binding energy here. So again, this is the inside of the conductor. Out here is the outside of the conductor. And that's how we essentially are setting up the structure. Now, the next piece here is that that's the copper atom structure. Now, let's talk about the band gap. So now, copper has a large band gap. So when I look at this, what we've said already here is that copper atoms have the ability to share electrons between adjacent copper atoms. In our box model, this is represented by the large band gap. So now what I'm going to try to do here is that picture-wise, we can draw many copper potentials as a single effective potential. With numerous weakly bound electrons. So let's see if we can do this here. So picture-wise, I'm going to imagine the following thing. I'm going to start with a box that looks like this. How am I going to draw this? I have a box like this, or a well like this. And then I know that in here, this is where I have all those inner electrons that can't move. And then I have the region where I have that weakly bound electron. So now what I'm thinking about here, because of the large band gap, I can combine all of these together. Okay, so I have this. I can just start, putting these all together here. And so you could imagine that now I have numerous ones. And what happens here, so what I'm saying here is that this represents numerous copper atoms. And then I'm going to model this as a single effective potential. So when I do that, the only thing that moves is that because of the large band gap, these electrons are easily transferred. So then I'm going to come in here and I'm going to say, okay, so this here represents all of the copper atoms right here. And so what you're seeing here is that this is the skin of the metal. And then these are the electrons that can be shared. So I have a shallow well. And so when I'm looking at these guys, you're seeing that I have numerous electrons in here. And so now that I have these numerous electrons, they, in the end, show that they have a tiny binding energy right there. So that's what I call a conductor. So in summary, our toy model gives us a picture of insulators and conductors. So if I look at this here, I'm going to say that this guy right here is going to be our conductor right here. And so if I look at this, I'm going to say that this is our conductor. We have lots of weakly bound electrons, and the fact that I have an effective single effective potential tells me that that represents the large band gap, and then they have small binding energies. On the other hand, I have insulators. So let me go grab this guy right here. So if I grab this guy here and I bring it down and I paste this here, what you're finding here is that this represents an insulator. And with the insulator, we're saying that these electrons are not readily available. And you could see that we've separated these electrons. They're not at the same, state as we saw over here. And furthermore, because I separate them, that means that they have a small band gap. And then here we could see that they have a large binding energy.